Hello and welcome. My name is Alan. Pull you up a seat, grab you something to drink. We're going to talk about more ideas and opinions of Albert Einstein. We are nearing the end of the book, so maybe 5, 6 more videos, and it'll be finished. Today we're reading a piece called The Common Language of Science. The blurb reads, broadcast recording for Science Conference in London, September the 28th, 1941, and published in Advancement of Science, London, February, Volume 2, Number 3. The first step toward language was to link acoustically or otherwise commutable signs to sense impression. Most likely, all sociable animals have arrived at this primitive kind of communication, at least on a certain degree. A higher development is reached when further signs are introduced and understood, which establish relations between other signs designating sense impression. At this stage, it is already possible to report somewhat complex series of impressions. We can say that language has come to existence. If language is to lead at all to understanding, there must be rules concerning the relations between the signs, and on the one hand, and on the other hand, there must be a stable correspondence between signs and impressions. In their childhood, individuals connected by the same language grasp these rules and relations mainly by intuition. When man becomes conscious of the rules concerning the relations between signs, the so-called grammar of language is established. In an early stage, the words may correspond directly to impressions. At a later stage, this direct connection is lost insofar as the same words convey relations to perceptions only if used in connection with other words. For instance, such words as is or thing. Then word groups rather than single words refer to perceptions. When language becomes thus partially independent of the background at impressions, a greater inner coherence is gained. Only at this further development, where frequent use is made of so-called abstract concepts, language becomes an instrument of reasoning in the true sense of the word. But it is also a development which turns language into a dangerous source of error and deception. Everything depends on the degree to which the words and combination correspond to the world of impression. That is, well, what is it that brings about such an intimate connection between language and thinking? Is there no thinking without the use of language, namely in concepts and concept combinations, for which words need not necessarily come to mind? Has not every one of us struggled with words through the connection between things uh, was already clear? We might be inclined to attribute to the act of thinking complete independence from language if the individual formed complete independent, or sorry, if the individual formed or were able to form his concepts without verbal guidance of this his environment. Yet, most likely, the mental shape of an individual showing up under such conditions would be very poor. Thus, we may conclude that the mental development of the individual and his way of forming concepts depend to a high degree upon language. This makes us realize to what extent the same language means the same mentality. In this sense, thinking and language are linked together. What distinguishes the language of science from the language as we ordinarily understand the word? How is it that scientific language is international? What science strives for is an utmost acuteness and clarity in concepts as regards their mutual relation and the correspondence to sensory data. As an illustration, let us take the language of Euclidean geometry and algebra. They manipulate with a small number of independently introduced concepts, respectively symbols such as the uh, integral number, the straight line, the point, as well as with signs which designate the fundamental operations, that is, the connections between the fundamental concepts. This is the basis for the construction and respectively the definition of all other statements and concepts. The connection between concepts and statements on the one hand and the sensory data on the other hand is established through acts of counting and measuring whose performance is sufficiently well determined. The supranational character of scientific concepts and scientific language is due to the fact that they have been set up by the best brains in all countries and all times, in solitude and yet in cooperative effort as regards the final effect. They created these spiritual tools for the technical revolutions which have transformed the life of mankind in the last centuries. Their system of concepts have served as a guide in the bewildering chaos of perceptions that we learn to grasp general truths from particular observations. What hopes and fears does the scientific method imply for mankind? I do not think that this is the right way to put the question. Whatever this tool is in the hand of man will produce depends entirely on the nature of the goals alive uh, in this mankind. Once these goals exist, the scientific method furnishes means to realize them. Yet, it cannot furnish the very goals. The scientific method itself would not have led anywhere. It would not even have been born without a passionate thriving for clear understanding. Perfection of means and confusion of goals seems, in my opinion, to characterize our age. If we desire sincerely and passionately the safety, the welfare, and the free development of the talents of all men, we shall not be in want of the means to approach such a state. Even if only a small part of mankind strives for such goals, their superiority will prove itself in the long run. In order to understand our law, or understand the law of equivalence of mass and energy, we must go back to the two conservations of balance principles which, independent of each other, held a high place in pre-relativity physics. These are the principles of conservation of energy and the principle of conservation of mass. The first of these, advanced by Leibniz as long as the 17th century, was developed in the 19th century, eventually as a corollary of a principle of mechanics. Consider, for example, a pendulum whose mass swings back and forth between the points A and B. At these points, the mass M is higher by the amount H, and it is than it is at C. The lowest point of the path, uh, and then at C, on the other hand, the lifting height has disappeared, and instead of the mass has a velocity of v. It is as though the lifting height could be converted entirely into velocity and vice versa. The exact relation would be expressed as mgh equals m over 2 times v squared, with g representing the acceleration of gravity. What is interesting here is that this relation is independent of both the length of the pendulum and the form of the path through which mass moves. The significance is that something remains constant throughout the process, and that something is energy. And at A and at B, it is an energy of position or potential energy. At C, it is an energy of motion or kinetic energy. If the concept is correct, when the sum mgh plus m times v squared over 2 must have the same value for any position of the pendulum. If h is understood to represent the height above c and v the velocity at the point in the pendulum's path, and such is found to be actually the case. The generalization of this principle gives us the law of the conservation of mechanical energy. But what happens when friction stops the pendulum? The answer to that is found in the study of heat phenomena. This study, based on the assumption that heat is an indestructible substance which flows from a warmer to a colder object, seemed to give us a principle of the conservation of heat. On the other hand, from time immemorial, it has been known that heat could be produced by friction, as in fire-making drills of the Indians. The physicists were for long unable to account for this kind of heat production. Their difficulties were overcome only when it successfully established that for any given amount of heat produced by friction, an exactly proportional amount of heat has to be expended. Thus did we arrive at a principle of the equivalence of work and heat with our pendulum. For example, mechanical energy is gradually converted by friction into heat. In such fashion, the principles of the conservations of mechanical and thermal energies were merged into one. The physicists were thereupon persuaded that the conservation principle should be further extended to take the chemical and electromagnetic processes, in short, could be applied to all fields. It appeared that in our physical system there was a sum total of energies that remained constant through all changes that might occur. Now, for the principle of conservation of mass. Mass is defined by the resistance that a body proposes to the acceleration, inert mass. It is also measured by the weight of the body, heavy mass. That these two radically different definitions lead to the same value for mass of a body is in itself an astonishing fact. According to the principle, namely, that masses remain unchanged under the physical or chemical changes, the mass appeared to be essential because unvarying equality of matter, heating, melting, vaporization, or combining into chemical compounds would not change the total mass. Physicists accepted this principle up to a few decades ago, but it proved inadequate in the face of the special theory of relativity. It was therefore merged with the energy principle, just as about 60 years before, the principle of conservation of mechanical energy had been combined with the principle of conservation of heat. We might say that the principle of the conservation of energy, having previously swallowed up that of the conservation of heat, now proceeded to swallow up the conservation of mass, and holds the field alone. It is customary to express the equivalence of mass and energy, though somewhat inexactly, by the formula E equals mc squared, in which c represents the velocity of light, about 156,000 miles per second. E is the energy that it contained in a stationary body. M is its mass. The energy that belongs to the mass, M, is equal to the mass multiplied by the square of the enormous speed of light, which is to say, a vast amount of energy for every unit of mass. But if every gram of material contains this tremendous energy, why did it go so long unnoticed? The answer is simple enough. So long as none of the energy is given off externally, it cannot be observed. It is as though a man who is fabulously rich should never spend or give away a cent, and no one could tell how rich he was. Now, we can reverse the revelation and say that an increase of E in the amount of energy must be accompanied by an increase of E over c squared in the mass. I can easily supply energy to the mass, for instance, if I heat by 10 degrees. So why not measure the mass increase or weight increase connected with the change? The trouble here is that the mass increase, the enormous factor c squared, occurs in the denominator of the fraction. In such a case, the increase is too small to be measured directly, even in the most sensitive balance. For a mass increase to be measurable, the change of energy per mass unit must be enormously large. We know of only one sphere in which such amounts of energy per mass unit are released, namely radioactive disintegration. Schematically, the process goes like this. An atom of the mass m splits into two atoms of the mass m1 and m2, which separates with tremendous kinetic energy. If we imagine these two masses as brought to rest, that is, if we take the energy of motion from them, then considered together they are essentially poorer in energy principle, or poorer than the original atom. According to the equivalence principle, the mass sum of M1 and M2 of the disintegration products must be somewhat smaller than the original mass M of the disintegrating atom, in the contradiction to the old principle of the conservation of mass. The relative difference of the two is on the order of 1/10 of 1%. Now, we cannot actually weigh the atoms individually. However, there are indirect methods for measuring their weights exactly. We can likewise determine the kinetic energies that are transferred into the disintegration products M1 and M2. Thus, it has become possible to to test and confirm equivalence formula. Also, the law permits us to calculate in advance from precisely determined atomic weights just how much energy will be released and any atomic disintegration we have in mind. The law says nothing, of course, as to whether or how the disintegration reaction can be brought about. What takes place can be illustrated with the help of our rich man. The atom M is a rich miser who, during his life, gives away no money or energy, but in his will he bequeaths his fortune to his sons M1 and M2 on condition that they give to the community a small amount, less than 1,000th of the whole estate, energy, or mass. The sons together have somewhat less than the father had. The mass sum, M1 and M2, is somewhat smaller than the mass M of the radioactive atom. But the sum given to the community, though relatively small, is still so enormously large, considered as kinetic energy, that it brings with it a great threat of evil. Averting that threat has become the most urgent problem of our time. So yeah, Einstein talking about using language to kind of break down the concepts themselves, because much of the concepts and ideas in science are not beholden to certain languages necessarily. They are used in representative formats. E equals mc squared. You don't have to know English to understand. You don't have to know German, Indian, Chinese, Russian, uh, you know, any particular language, because we understand it's within formats. But uh, we have to try to keep it in these concepts, but we also need to break it down easier so that everyone kind of understands. But he's also in the end kind of giving a warning about how uh, nuclear disintegration is part of the effect of dropping atomic bombs. But yeah, he talks much about the principle of E equals mc squared. He uses that a lot, which is his famous uh, equation, which is actually a condensing of a smaller equation or a larger equation. But what's usually cited is energy equals mass times speed of light squared. Um, there is a much larger equation. I'll try to find that and put that in the description below the video. But yeah, um, it's basically talking about uh, how science really belongs to no one language, but because it needs to be commonly understood. And so much of it is within the ideas and representations of concepts. But yeah, that'll be it for this episode. As always, educate thyself. Think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.